So let's go ahead and move on with a couple of other distinctions for specially named antigens. Now, an antigen, remember, is considered a large foreign molecule that's not normally present in your body that will cause you to mount an immune response. But an antigen since it's a large molecule, it has very distinct spots on it that we call antigenic determinants that are the actual areas of this molecule that the antibody or immune response will recognize. And we have some very special antigen types that have special names because they are commonly associated with certain things, such as an agglutinogen is what we call the antigen that we will respond to on red blood cells. And if we have a red blood cell, and there are 4 different types of red blood cells, correct? And what's one type of red blood cell? You guys have already done the activity, so A. And so the agglutinogen on its surface is A. And then for B, the agglutinogen on its surface would be B, and that's the term for its specific antigen. If you're O, you have neither, and if you're AB, you have A and B agglutinogens on your surface. So that is a special name because it causes the agglutination or clumping out of the blood cells if we have a transfusion reaction that actually occurs, for example. Allergen, that's the special type of antigen which will cause an allergic reaction. And then we have a very special type of antigen called MHC MHC proteins or antigens. These are self-antigens, and M for major, H for histocompatibility, C for complex. So we're going to discuss these MHCs in just a moment, but these MHCs give you what's called a cellular fingerprint. And remember, we use fingerprints to identify people. And so what this is telling you, we can identify who these cells come from by their MHC pattern. And this is very important because the reason histocompatibility was chosen, it was chosen for organ transplantation. Because if you want to take an organ out of somebody else and put it into another different person, the donor into the recipient, you want that organ to be as compatible with the recipient as possible, correct? Major histocompatibility complex. And so this is what is tested when they tell you whether or not the organ is going to be compatible or accepted by the recipient. And the less compatibility, the more likely the rejection. And this is the rejection process that we'll actually be going through when we actually go through some more information about histocompatibility in itself. Let's go on to now cells of our immune system or the adaptive branch. The B cells and T cells, they're both lymphocytes, but B cells are found in our fluids, and that's why we talk about that as humoral immunity. They become immunocompetent in the bone marrow. So that's where they get their training or indoctrination. And then the T cells become immunocompetent in the thymus. Yes. All lymphocytes originate from bone marrow, but where do lymphocytes go besides the blood? Soft tissue. Let's be, how about lymphoid tissue? And you remember what lymphoid tissue is? Oh, come on. It's not that hard. We just had it in the last chapter. One of them starts with lymph nodes, spleen, thymus, tonsils. Yeah, so lymphoid tissue, lymphocytes. That's why it's called lymphoid tissue. Isn't that what we actually talked about? T lymphocytes and B lymphocytes inside these lymphoid tissue. And so if we have an area called germinal center, doesn't that imply mitosis? And so basically we're actually having lymphocytes that actually can proliferate inside lymphoid tissue if properly stimulated. But originally, they all originate from the bone marrow. And then the T got trained or immunocompetent in the thymus. APCs stands for antigen-presenting cells. So these cells are macrophages, dendritic cells, which are the macrophages associated with our skin, and also B cells can act as antigen-presenting cells. What these cells will do, they engulf the pathogen, they digest it, remember the phagolysosome thing, and then present this to a T helper cell. The dendritic cells are kind of really good at this, so I put a little asterisk by the dendritic cells. Receptor complexes, major histocompatibility complex. So let's talk about some other complex that are on the surface of our cells. And these are receptor complexes. So they are on the surface of lymphocytes, and they are designed to bind only one specific antigen or antigenic determinant. So instead of saying antigenic determinant often, I will say antigen, but you have to realize that's the part that we are going to react to. So we have TCRs, which stands for T cell receptors. And we have BCRs, which are for B cell receptors. Let's take a look at this picture down below, and we'll start with the BCR, or B cell receptor. The BCR, B cell receptor, always looks like a Y. And that's one way you can always identify a B cell. They always have these Ys on their surface. So that's a B cell receptor, and it has binding sites here at the ends of the Y that are specific for only one type of antigenic determinant. And they're all the same. So all of these Ys here are all the same. And so these are all binding sites for a very specific antigen. That's a B lymphocyte. Now let's take a look at the T lymphocytes. And I want you to realize we're going to have to learn about two specific T lymphocytes. One T lymphocyte has what's called a CD4 protein on its surface, and that is going to be a helper cell. So CD4 is helper cell. The other lymphocyte will have a CD8 protein on its surface, and that's always going to be associated with a cytotoxic T cell. So this is a surface marker that will actually tell you if I'm talking about a CD4 cell, I'm talking about a helper cell. If I'm talking about a CD8 cell, I'm talking about a cytotoxic T cell. If you take a look at the picture, here's the T cell receptors next to the protein, the surface protein CD8 or CD4. So that's the T cell receptor. They look like a cone in this cartoon here, but I want you to realize they're supposed to look the same. They're just associated with a different cell and a different color. And so they will bind a very specific, just like up above, very specific antigen in that little cone. So that's the binding site. The binding site on the B lymphocyte was the ends of the Y, the two arms of the Y, but the binding site for the antigen are these little cones right here on these two T cells. They look the same because it's the same type of antigen that's going to bind to them, but what these cells do after the binding is very, very different. Let's move down to MHC, because we were going to talk a little bit more about this. Major histocompatibility complex. Cellular fingerprint. We have two classes of MHC. We have class 1 MHC and we have class 2 MHC. Class 1 MHC is on all of your nucleated cells. So what cell does not have class 1 MHC on its surface? Red blood cells. So MHC is on every cell except for red blood cells. And MHC is a site that I liken to the class 1 MHC is, because it says it holds and displays an antigen. So I'm going to ask you to liken class 1 MHC to a flagpole. And when it displays an antigen that is self, then what flag will be displayed? United States flag. But if it's displaying a foreign antigen, it will not be the United States flag anymore, correct? It's probably the Russian flag. But that's what's important. Class 1 MHC is designed to tell the immune system cells that are going around, always checking things out, also the natural killer cells going around, always checking things out, that I'm okay, I'm me, nothing's wrong with me, or I'm not okay, something's wrong with me, I have been invaded. I have been invaded by a virus, and I have a viral infection trying to actually take over my machinery and spread, or cancer, for example, or somebody else's cell in a transplant organ, correct? Because if it's a transplant organ, will that MHC1 look exactly like the recipient's? It can be different, and it's that degree of difference, again, that's important for transplantation. So that's why I like to liken class 1 MHC to a flagpole, and then the antigen is the flag, and it's self or not self, which is foreign. So again, MHC1 is a surface receptor. That is designed to display the cell's health. And so I'm okay, my flag, or I'm not okay, a foreign flag, something that you're not used to seeing. So MHC1, all cells except for red blood cells. Class 2 MHC is only on APCs, antigen-presenting cells. And Class 2 MHC is designed to be presented, the antigen that's on Class 2 MHC is designed to be presented to CD4 cells. CD4 cells are helper cells. So these are T little h or subscript H cells, not little h, but helper cells, so CD4 cells. And so they will be displaying a foreign antigen because this is what their job is actually all about. Their job is actually to take foreign material that has actually invaded you, and that's why they're antigen presenting cells, and present them to the commander, so to speak, so that we can actually get some sort of military action going. So do APCs only have class 2 MHC? No, they also have class 1 MHC. So APCs have both, correct? And the other cells do not. So this is what validates their existence. These are trained specialists. So they are trained to recognize the foreign material and to take it to the proper cell that is going to help to cause you to mount an immune response. So these guys are very special. So APCs designed to be the only ones T helper cells respond to. And it has to be MHC2 with foreign antigen. And what I'll do to kind of help designate foreign antigen, as I write notes here, AG with an apostrophe by it. Maybe that will help with designating that's a foreign antigen. Because now we're talking about antigen surface markers that are actually part of you. So we've gone from antigens are things that don't belong to you to actually that you have your own antigens. And you are then taking, your body can recognize your own surface antigens, but if we take your organ out and put it into somebody else, it's now foreign antigen material. And so we'll put a little apostrophe by antigens that are definitely foreign. Taking a look at this cartoon down here, let's go down to the bottom explanation. CD4 interacts specifically with class 2 MHC molecules, and CD8 interacts specifically with class 1 MHC molecules. So CD4 T helpers, CD8 are the cytotoxic T cells. Those are one that are actually going to engage in what I call hand-to-hand combat. So in order for this nucleated cell here, one thing we know, if it's a nucleated cell, it has which MHC on its surface, no matter what cell it is. MHC1, automatically. As long as it has a nucleus, we already know it's got MHC1 on it. But if we are going to communicate with a helper cell, what other surface marker will that cell have on it? MHC2. And if we have MHC2, that makes it an APC, correct? An antigen-presenting cell. So that's one of the things to realize. If we are communicating with a helper cell, we must be an antigen-presenting cell and have an MHC2 here. Our notes here say, right down there, it says class 1 or class 2 with an antigen in it. So we have some sort of flag or foreign material, self or non-self, actually on that. And then T cell receptors, if we have if it's got a surface marker that's a CD4, that's a helper. If we have a surface marker that's a CD8, that's a cytotoxic T cell. And that's why we can actually use this kind of generic look, because the T helper and cytotoxic T cells have a very similar construction, except for that surface marker CD8 and CD4. Cell-mediated immunity are T cells, which is what we've been talking about so far. When we talk about helper cells, surface marker is CD4. Activation of these cells is by APCs only. This is a two-step process. I think you already have this in the notes. It's been a little bit modified and didn't quite turn out the way I was hoping it would. But activation of helper cells, in other words, getting them to do their job. So activation is getting them to do their job. It's a two-step process. T helper cells help coordinate immune response. They do this by helping B cells plus T cells to clone and activate, let's see, and do their job, which is a complete activation. So activation equals presentation via MHC plus co-stimulation. Let's go down. This is in a different order in your notes. It's on another page probably. Go down and find this cartoon or diagram in your notes. Let's move on over to the helper T lymphocyte side of this, because this is what we're going to talk about, and then we'll talk about the cytotoxic T cells. We know if we see APC here, and it's going to a helper cell, we know the helper cell has CD4 on its surface. We also know if we are an APC communicating with a T helper cell, we are using class 2 MHC to communicate with that helper cell. It is loaded with an antigen, and if we're needing help to fight the pathogen, that antigen is not self-antigen. That's a pathogenic antigen. And so we have this interaction with the APC and the T helper cell. So the T cell receptor, TCR, is going to bind this antigen that's presented to it. It will not bind antigen that's not presented. So even if antigen is floating around, it will not bind. It actually needs the APC to formally present it to and bind. Now, when you bind, so that's the first step, presentation. The second step is co-stimulation. And second signal co-stimulation chemicals are going to be released that are going to actually cause that helper cell to then go to the next level, which is full activation. So we have to present and we have to co-stimulate all of our cells actually in order for them to do the process of doing their job. Part of doing their job is cloning. So this multiple arrows here is cloning. So now that activated helper cell is going to clone, which means make a whole bunch of its cells that's actually ready to go out and do its job, which is to help everybody else clone and do their job. That's what a helper cell does. A helper cell goes out and helps all other cytotoxic T cells and even B cells go out there to clone and do their job. The important thing about step number 1, presentation, it's like a car. So we're going to the car and we want to take the car someplace, to have the car take us someplace, or take the car someplace, either way. So when you get in the car, what's the first thing you do if you want to go somewhere? You start the car, okay? So you put the key in and turn it on and you start the car. Well, is that all you do to go someplace? Yeah. That's right. That's why this is a 2-step process. We have to, A, put the key in, which is get the receptor and antigen, interacting. So we have to put the key in and start the car, but then we have to put it into gear to drive someplace. And that's co-stimulation. And so when you interact, when we present, that's interaction, that's starting the car. And then when co-stimulatory enzymes are released onto that helper cell, for right here, for activation of this helper cell, we're putting it into gear and we're getting out of the car, or the T helper cell, what it's supposed to do, which is to clone, which is to make identical copies of itself that can go out and then co-stimulate other cells so that they can clone and do their job. So do you see, this is kind of the master controller of the process of making clones of cells that are going to be able to recognize a very specific antigenic determinant. So these cells are only designed to respond to a specific antigen or antigenic determinant. When they clone, they will make two types of cells. They will make active T helper cells and memory T helper cells. Active is doing their job, and memory is like, I know what to do, but I'm not doing it because I'm going to wait for another time that the pathogen is in the system. And if you're cloning a bunch of memory cells, that means you have more memory. And these cells, these memory cells, guess where they go? Guess where these T cells go? Lymphoid organs, yes. So that previously you didn't have these memory cells. Now you have these memory cells that are ready to go at the drop of a hat. And so you put them out in all of the lymphoid organs to live there so that when the pathogen comes into that area, they know what to do, and they are memory cells, so they know what this is, and what they'll do is they won't just sit there and be a memory. They will then actually go ahead and actively clone and actually do their job. So that's an important thing. Memory cells are there for a second exposure, and they're ready to go without this process that we're actually talking about here. Now let's go look at the cytotoxic T lymphocyte. Realize the process is very similar. However, the CD8 cell, cytotoxic cell, doesn't need MHC2. It responds to MHC1. So let's take a look here. We have, and that's what's really nice about an APC, an antigen-presenting cell. It has MHC1 and MHC2 on it, correct? So an antigen-presenting cell can also go over to a cytotoxic T cell and say, this, I just talked to the helper cell, and now I'm talking to you guys, which are going to go out there and do hand-to-hand combat, because the memory cell just makes you clone and turn you on, you know, and get you ready to go into gear. But now we need to actually fight, and that's what cytotoxic T cells are for. They are actually for the fight. So an APC will take its MHC1 loaded with the foreign antigen to a cytotoxic T cell, and I want you to notice there's this word. We're going to talk about that word in a moment, naive. When you are naive, what does that mean? You don't really know what to do, isn't it? You know, you've never done it before. That's when you're naive. And so that's what this is referring to. When you're naive, you've read all about it. You know, when you get into a nursing program and you've studied all the material on how to catheterize somebody, okay? You know in your head what you're supposed to do, but you haven't done it yet, have you? So you are naive until you actually catheterize somebody. And so that's what naive means here too. Naive means we know what to do. That's why we have these sites, but we have never done it yet. And so we have to go from being naive to activated. So our naive cytotoxic T lymphocyte has never gone and killed anything before, but it knows how to kill. It's just never done it. So the APC and the T cell receptor on the cytotoxic T cell, they have that antigen sharing. They do the passover, handoff. And so that's like putting the key in and turning the car on. But in order for us to go and clone and then go out and kill, we need the second signal, which is the same thing that the T helper cell needed. It needed co-stimulation. That's what those little dots are all about. Co-stimulating enzymes are going to put it into gear, and when we put the naive cell into gear, it will clone. So again, we get cloning, and we will clone into activated cytotoxic T cells and memory T cells. And so our lymphoid organs are full of T helper cells with memory and cytotoxic T cells with memory. Because the more co-stimulation you give, the better cloning and the faster action you get. So This is an important aspect. Again, we are cloning into activated cells and memory cells. If you're activated, that means you'll go out and do the job. With the cytotoxic T cells, once they become activated and they're actually ready to fight, the only way they can recognize who they're supposed to attack is if the cell has the MHC1 on it loaded with the pathogenic antigen that it was just, presented. You guys follow me with that? It's a complicated story, but it's what keeps you from fighting yourself. You only want to fight the pathogen, right? You don't want to accidentally fight yourself. And so this is a process for that. Let's go and add some notes to the cytotoxic T cell. We know it contains a surface marker CD8. It is designed to fight cells with abnormal MHC1 antigens. It will not fight an APC. It will fight cells with an MHC1 that has got the abnormal antigen on it. Again, this is a two-step process. For full activation. And full activation equals cloning to produce activated or fighting cytotoxic T cells plus memory.
So is the original cytotoxic T cell doing anything other than cloning itself and cloning those active ones? Is it going to go out and fight, or is it only going to clone?
It is going to clone. The naive cell is like the parent
Right.
that's going to create the clone yes,
Okay.
create the army.
Right. So that
So-
initial cell that gets shown the flag, and it says, okay, now you've got to start being active. And
Which is a
use the
cloning
clone.
process.
Right, which is the clone.
And they're mean, angry clones,
Right.
and then clones that remember how to be mean and angry.
Right.
Which are the
So
memory
those are the
cells.
two codes, and then they're all ready, and they just march out and go through their things.
Correct.
But that original cell just keeps cloning and making more.
Yes, the original cell is the one from which all others come from.
Okay.
So we'll have AG prime or comma equals abnormal antigen in our notes. And so we need a cytotoxic T cell come into contact with an APC/MHC1 that is loaded with antigen prime, or a foreign antigen. Plus, in order for full activation, this is not enough. Remember, this is putting the key in, turning the engine on. We actually now need T helpers, co-stimulatory enzymes. When we have all that, we then go ahead and actively clone, and we create a whole bunch of fighting machines and machines that are ready to fight another day.
So that's the queen cell.
Yes, the naive cell.
So
And the activated cytotoxic T cell looks for any cell, ordinary cell, with MHC1 antigen prime, that abnormal antigen, the one that it was shown. So it's very specific for that antigenic determinant. It's very specific. Once it finds that cell, it will bind to that cell just like we had the binding with the APC and our naive cytotoxic T lymphocyte. The next thing that will happen is we want to kill that cell because it's wrong. It doesn't belong here. It's either cancerous or virally infected, or maybe it's somebody's transplanted organ. but that's the way our body works. So the cytotoxic T cell will bind tightly to that cell that's got the problem. It's antigen in the MHC1, and it releases perforin. Perforin is a protein that's designed to poke a hole, polymerize and create a hole there. And what's interesting, the T cell will bind, release perforin and granzyme, but they actually go in a very specific sequence, because after it drops off its perforin and granzyme package, it leaves, because it's going to do the same thing to another cell that looks like this cell with the MHC1 abnormal antigen marker. So after it leaves, and this is kind of like it's dropping off a timed bomb on these cells. That perforin polymerizes, makes that transmembrane pore for then the granzymes to enter into the pore to cause the apoptosis of that cell. And it will die in approximately 2 hours. Suicide, hara-kiri, whatever. Another thing about cytotoxic T cells, they can secrete this TNF, tumor necrosis factor. We're still working on the steps of this, but that's where tumor necrosis factor comes from. It comes from activated cytotoxic T cells. Now into some definitions that we already kind of touched. Naive cells, any lymphocyte that has not been fully activated or challenged. Challenge and activation should be considered the same. So challenge equals fully activated. So our T and B cells can be naive. They are programmed to respond to a specific antigenic determinant. But if you're naive, you have never encountered it before. But the APC is bringing it to you, saying, we now have this pathogen in our body and we need to mount an immune response, because that's what APCs are going. And the helper cell will not listen to any other cell because it only listens to APCs, which have MHC2 on their surface. So that's kind of like, you have to realize the lymphatic system has a lot of military correlation. And if you are a civilian and you go to the general and saying we're being invaded by Russia, do you think the general's going to listen to you? No. So this is what this is. This is why this is a very chain of command. This is, in other words, saying this is a reliable cell that is telling me that this infection or problem is present, because it literally has pieces of the problem that it has encountered the problem, it has digested the problem, and now it is showing me the problem. And it doesn't believe the other cells, because they could sometimes be Chicken Little and say the sky is falling, and we're not going to listen to Chicken Little. So naive cells, they know what to do, they've just never had to do it before. But now we're going to do something, and now will be a challenged or fully activated cell. The other thing about naives, when we actually activate them, remember we're going to make clones, because activation is a cloning process. So we're going to make clones, and there's going to be 2 types of cells. The bulk of the cells are going to be fighting cells, and the other guys are going to be memory cells. And those are going to be very similar to what I refer to those guys that are on active duty. They aren't actually being deployed. but they are on active duty and can be called into actual deployment if needed. Memory cells. They are indeed produced during a cloning to fight in the future. All activated cells, T or B cells, PD produce memory cells. They are always ready to fight, but because their memory cells have been instructed to wait until next battle / exposure. Memory cells, are they naive? No, they are not naive. Memory cells have seen the enemy and they know actually what it is. So, able to respond faster and more efficiently. Next time. Okay, so there's a war going on, and you've won the war, and you need to tell everybody, calm down now. And that's what Treg cells are all about. So T regulatory cells are designed to suppress the immune system. And so they will come in and they will actually take all of these activated cells and help them turn their machinery off for the fight, since it's no longer there. That is cell-mediated immunity. Now let's talk about the humoral system, which is our B cells. Antigen challenge. So this is in the humors, in the fluids, and so antigen challenge will usually occur in the spleen because the problem is in the bloodstream, or in a lymph node because the problem is in the, what I would call, soft tissues, because lymph nodes are everywhere, correct? Actually, we know where they're concentrated, but they're actually everywhere. So the lymph node is hooked up to the lymphatic system, and so that's if we get the infection in the soft tissues. Let's take a look at how B cells are activated and that they also clone. So remember, T cells clone and B cells clone when they're activated. And when they've never cloned before, that means they're naive, right? We can always tell a B cell because their B cell receptor, or BCRs, always look like these Ys. And that's a very specific antibody that we'll talk about in just a moment. This is, again, a two-step process. So the antigen is going to bind to a very specific receptor on the B cell, which is that Y thing. And up in our cartoon, you see the antigens are the teal colored balls. So here is the antigen attaching to the ends of the Y that's actually sticking out there. And so that's our binding. And what's interesting about this picture here is that antigen is not being presented to the B cell, is it? So T cells have to have presentation, where B cells, because they're also APCs, antigen presenting cells, don't have to have a presenter cell to them because they're a presenter cell. So we have the antigen binding to the B cell receptor, and then we have a T helper cell that's been activated. That means that cell has cloned, and how do T helper cells help everybody else clone? It's the co-stimulatory enzyme. So remember, the co-stimulatory enzyme is putting you into gear so that you can go someplace. So we see in our picture here, this is our B cell, and this is our T cell, T helper cell. The B cell is presenting, because it's an antigen presenting cell, it is presenting to the T helper cell, and it has to do it via the MHC2 protein complex surface marker. And so that's one thing too. You have to realize that the macrophages, they engulfed their pathogen and brought it in and then loaded up their MHC2s. Dendritic cells and macrophages have MHC2s. So because they're macrophages, they engulf the pathogen, they digest it, and then they take pieces of this abnormal pathogen and load it up on the MHC2. Well, we still have to present to a T helper cell via an MHC2. And so what will happen is the B cell wants to clone, but cannot clone without the co-stimulatory enzyme from a T helper cell. So it has its little Ys, it has its antigens that it attached to it. And what's interesting is that little antigen receptor complex gets brought inside the cell, and then that antigen gets properly disassembled and put onto the MHC2 on the surface of the cell, which will then interact with the T helper cell. I know this is all complicated, but if you can get MHC2 to helper and helper co-stimulatory to help itself, if you're an APC, this B cell is an APC too, but this B cell does not want to just, I know this is complicated, this B cell doesn't just want to turn on the helper cell. The B cell wants the helper cell to turn it on because the B cell wants to clone, because it's a lymphocyte, and lymphocytes are part of the immune system. So this B cell is presenting to the T helper cell. If this T helper cell has been activated, as this indicates, it is then going to go ahead and put in the second step, the co-stimulatory enzyme, on the B cell, which will now clone. So the B cell will clone and create a whole bunch of activated B cells and memory B cells. The important thing about the activated B cells is activated B cells produce antibodies. So in the notes, the steps show antigen binding on the B cell receptor, B cell endocytosis, the receptor antigen complex. It then takes it to the T helper cell, and this incompletely activated B cell, because this B cell needs the co-stimulatory enzyme, and that's why it says incompletely activated. So we needs, so B cell needs co-stim enzyme from T helper cell to complete its activation. Once the B cell has received the co-stimulatory enzyme, it will now clone. It will produce a whole bunch of cells called plasma cells and a whole bunch of cells called memory cells, but the plasma cells will definitely outnumber the memory cells. And the plasma cells are responsible for making antibodies. And antibodies have that Y shape.
So when the B cell goes to the T helper cell, it's like he's going not only to show the B helper cell, but also to be put on active duty.
Correct. It's I want to fight, but I can't fight until you tell me to fight. And that's indeed why T helper cells are so important, because they give the cell the permission to fight, but also it's cloning. Because if you only have one fighter, how easy is it to win the war with just one when you have a whole army of them. And so we need a whole army of active fighters, and that's the cloning process. Now let's talk about this memory thing, immunological memory. Primary immune response and secondary immune response. Primary immune response is indeed our first exposure of our T cells to the antigen. And it takes 3 to 6 days to start. AB is our abbreviation for antibody synthesis. So our immunological memory that we are talking about right now is for our B cells, because we're talking about antibody synthesis. But you have to realize we also have to activate a helper cell before we can turn on a B cell. Are you guys following me with this? Do you see the complexity of this chain of command? So B cells can't clone until and make antibodies until they have a T helper cell that has also been activated to get them to start their cloning and antibody production. So it takes time for all of this to occur. You follow this kind of complicated chain of command. And peak antibody production, PDTN, is 10 to 14 days after exposure. So this is our primary immune response. First exposure to the antigen. A whole bunch of activation going on here. Helper cells, B cells, and we want antibody production. And in order to get any antibodies, it's going to take 3 to 6 days to start this up. Some people are really fast at this. Other people are a little bit slower. That's why we have 3 to 6 days. But peak antibody production, in other words, I want you to realize antibodies are like missiles taking out the bad, or bullets taking out the bad guys. You know, so peak antibody production is 10 to 14 days, and the more antibody you have, the sooner the infection or the problem is over, correct? And so this is primary immune response. And so when you get sick, this is telling you if you have never encountered this bug before or this virus before, you know, such as influenza, you will feel awful for 3 to 6 days because you have no antibody production, depending upon who you are. Okay. You will feel awful because it's overwhelming you at that time, but then 10 to 14 days, after 3 to 6 days, you go, well, I'm not so bad, but I'm bad. And you feel bad until peak antibody production occurs, because when peak antibody production occurs, you are getting rid of the pathogen, the influenza virus, out of your system. You are eradicating it. And so peak antibody production is very important for making you feel like you're going to live. And yes?
So does that then mean that you're truly not infectious until 10 to 14 days after exposure?
So the question is, how long are you infectious or contagious? Probably is your question. And indeed, it's about 2 weeks out for a primary immune response. However, if you have seen this pathogen before, because you now have memory cells, right? You can now, because you have activated memory cells of both the B and T cells. You guys follow me here? You have activated memory cells of B cells and T helper cells. Easy to trigger the cloning. And you know, if you're triggering cloning, you're already activated, and you will get peak antibody production in 2 to 3 days. And it's significantly more than the first time around. So when I say peak antibody production for the primary exposure or primary immune response, I'm telling you it's this level, and when I'm talking about peak antibody production for the secondary immune response, where you've seen it before, it's this level. So you have a whole lot more so fast that you actually start to think that you weren't sick anymore. So what happens is that you think you're getting ill and you feel really crappy, but the next day you wake up and you go, oh, that echinacea worked for me. Was it really echinacea? It was that your system has seen it before, and now you're having a secondary immune response, and it's wiping it out ASAP. So you start to feel better.
So,
Which is why we give you something as I call the early warning system. Vaccines. Because vaccines give you the primary immune response, and you're not sick. You guys follow me on that? Because we're not giving you that agent that's going to make you sick. We're giving you the antigenic determinants. So they're not the whole living virus or whatever. They're antigenic determinants, which you will then mount a primary immune response so that when you actually are exposed to the influenza that the vaccine was for, that you developed a primary immune response to, you'll get a secondary immune response and you'll think you're getting sick, but the next day you go, oh, I think I'm better. You know, it wasn't so bad.
so are antibiotics really necessary? Or
Antibiotics are only for bacteria. And most of our immunizations are antiviral, but not all of them. Some of them are also bacterial too, but most of them are antiviral. The meningitis vaccine is for meningococcus, which is bacterial, and it's for certain antigenic determinants that are part of the polysaccharide coat of that bacteria. So let's talk about that now. Active and passive humoral immunity. So we're talking about, when I say humoral immunity, we're talking about antibody production. Okay. Active immunity. 2 ways you can actually acquire immunity, which is naturally. You can let somebody cough on you, sneeze on you. You can take your child to somebody who's got chicken pox and have a play day with that kid. That's active immunity, because then they will acquire the infection and have a primary immune response, which is kind of mean, because that means they have that lovely 2 weeks of not feeling great. Artificially acquired active immunity is indeed injection of dead or attenuated pathogen or parts, which we all know is called a vaccine, also called an immunization. Passive immunity. So remember, we're talking about antibody production. So how can you passively get antibodies in your system?
Parents,
Pardon?
genealogy, parents.
Genes? Well, not really. Because how can you passively have a whole bunch of antibodies in your bloodstream? Is if somebody gave you a whole bunch of antibodies to put in your bloodstream.
Like milk.
Breast milk, yes. Yep. Mom makes the antibody and gives it to the infant, yes. Also, then another nice thing about mom is actually making antibodies for whatever's in her environment, correct? Whatever she's getting exposed to, she's got a normal immune system, she will make antibodies. Even if it's a primary exposure, okay? Primary exposure, secondary exposure, it doesn't matter. If you're having a normal immune response, you will make antibodies. The rapidity and the level of antibody production depends upon whether you've seen it or not, correct? So mom is always making antibodies, and when she's pregnant, she is always communicating with her fetus how? via the
So those-
placenta. And what's important is these antibodies can cross the placenta. So if mom is making antibodies, what does that tell you about the baby? Has mom's antibodies. And that's another reason why newborns can be exposed to unfortunately goofy people who bring their sick kids over to see a newborn baby. Because mom has already beefed them up with antibodies. And so that's why you say, oh, babies don't get sick. Yes, thank goodness for mothers. You know, that's all I can say. Mothers are making the difference here because the mother was the one that was exposed to the antigen or the pathogen. You guys follow me? The mother was the one that made the antibodies to the antigen and pathogen, and the mother was the other one that mainlined it to the baby. So these antibodies are floating around in the baby's bloodstream when the baby is born. And so that's why babies are actually protected quite well in their first several months of life because mom gave them the protection. That's passive immunity. Did the baby make the antibodies? No. Active immunity means you make the antibodies. Passive immunity means somebody else put antibodies in you. Mom does it via the placenta or via breastfeeding. What's another way that we can get passive immunity? Let's see. How fast of a primary immune response do you think you actually have to rattlesnake venom? How about to rabies? How about to botulism? So if you get bit by a snake, a rattlesnake, what are you going to do? Anti-venom. What do you suppose anti-venom would be? Hint, hint. Passive immunity. Yeah. It is antibodies to that bad shit. You guys woke up, didn't you? You know, we're an hour into the lecture and you're still with me. Yes.
Do passive immunity, does it last as long as active immunity does?
Does passive immunity act as long as active immunity? Passive immunity does not, because active immunity means that you can always make more antibodies no matter what the exposure level is. So passive immunity means we are giving you a bolus or a finite amount of antibody. And like mom gives you antibody all the time, she's making it, but once you're born, are you getting any more antibodies from mom unless she's, you know, say she's bottle feeding, you know. So no, so those antibodies are only going to float around in that baby's bloodstream for a while. And it can be, you know, weeks to months, depending upon the antibody type. So same thing with when you get anti-venom. That anti-venom doesn't stay floating around in your bloodstream for a really long period of time. It's weeks to months that it will actually be there. So we need to get passive immunity to these things which can kill us. First-time exposure. And so that's what we're talking about here with our anti-venom.
There's no memory cells that activate with passive immunity.
Correct. There is no such thing as memory with passive immunity. That's why if you get bit by a rattlesnake again, what do you have to do? You have to go back for another shot. That's right. And you don't want the other shot to be like the first shot. Let's talk about how you make anti-venom. Okay. Does anybody know who we harvest the anti-venom from? Well, we take the venom from the snake, and where do we get anti-venom? Okay, so you take where do you get the anti-venom? Well, you have a horse. You inject venom into horse. The venom is snake bite antigen. I could say the same thing, right? Snake bite antigen. And if you did it right, what happens to the horse? If you did it right, do you want the horse to die? No, you want the horse to live. Because if the horse lives, you know what the horse did, right? Created antibodies, that's right. So it creates antibodies, and then do you want to harvest, after 2 weeks on that horse? No, what do you want to do? Immediately? Well, you won't get, how much, and what's the antibody titer going to be in that horse immediately after you inject the venom in it? Down on the floor, right? 3 to 6 days before you even get any antibodies in us. So it's going to be relatively similar. So you want to get the venom from the horse in 2 weeks. But what if you want a lot of anti-venom? Do you want to do that? What's up?
Say 2 weeks because it starts killing off our antibodies, right?
Yeah, but what if you want a lot of anti-venom?
Then you probably would inject it again.
That's right. If you want a big bang for your buck, 2 weeks later, you're going to hit them up again with venom. You'll inject it into them again, and what's going to happen to our antibody titer?
It's going to go really high because of the
Yeah, through the roof. Isn't that what you want? Don't you want a whole bunch? So that's what they'll do. They'll inject the venom into the horse, and the horse will have primary immune response. Then later, inject again. Because we like secondary immune response. Because we know we don't have to wait as long, we don't have to feed the horse as much, and we know we'll have a really high titer of anti-venom or snake bite venom antibody from the horse. So then you inject this anti-venom into the human ASAP, right? And so they have this anti-venom hanging around in a bottle in their emergency room, typically. Not in Idaho, but, in other states where there's lots of rattlesnakes. Now, let me ask you, though, is that anti-venom, those antibodies that are being injected into you, going to be actually viewed by you as good or bad by you, your immune system? Bad. So what will you do when somebody injects anti-venom into you? What will you do to the anti-venom? You will get a primary immune response to the anti-venom. So that's another reason why they really don't like people to do this rattlesnake handling, because they're going to have to learn to make their own antibodies, because the anti-venom will also become ineffective the more you have to actually inject somebody with that, correct? Because the first time you inject them, you'll just get a primary immune response, but then the second time you inject them, they're also, because isn't antibodies from a horse in you considered foreign material?
Yes.
Yeah. So that's the catch-22 when you have to have these other methods to actually handle this process or problem. So our notes in here say active and passive immunity, a little chart here. Active immunity, we produce. You produce the antibodies. Naturally acquired, you get the exposure. You have to go through primary immune response. Artificially acquired, well, you don't feel the primary immune response because the shot is not designed to make you ill, but you will have a secondary immune response because of the vaccine, and you won't feel ill for very long at all.
Except, why is it then that there are times when you get injected and you then feel like crap within a very short time?
That's your innate immune system.
Okay.
So remember we talked about inflammation and stuff like that? So this is indeed, the vaccine is foreign material, correct?
Yeah, you need
It's
to know
being-
it's active.
yes.
Still foreign.
The foreign material is being injected into you, and it's causing your macrophages and your neutrophils and all these mast cells and all these guys to actually respond to it. So that's the,
Considered foreign.
yeah, it's foreign. Isn't a vaccine? I don't care what it is. Any vaccine is foreign material, correct? We are trying to stimulate an immune response, but that doesn't mean that we won't sometimes get a very aggressive, innate response. So that's why some people get fevers, because remember, is fever innate? That's why we get those fevers and things like that. So that's why people will have those responses to vaccines. I'd love to talk to a bunch of anti-vacciners, but do you think they'll ever listen to me? No. They don't want to hear this stuff. Okay, so passive immunity, we have no production of any sort of memory cells. We do not produce the antibodies, so if it's naturally acquired, that means we got it from somebody we like our mother. If it's artificially acquired, that means that we actually were given antibody in the form of antivenom. Quickly, let's take a look at antibodies. We call antibodies immunoglobulins. Remember immunization? Now we call them immunoglobulins. Globular refers to protein. You guys remember we talked about globular proteins? So these are very interesting protein molecules that are part of our immune response. So an antibody looks like a Y, which is what this picture is right here. It looks like a Y to me, that big picture down there. And you have to realize it is a polypeptide, and there are 4 chains. Take a look at this. We have 2 light chains, one here, one over here, and 2 heavy chains. So that's 4 polypeptides. So at the Y area are where the 2 chains are located, and we call, when we take a look at this Y, it's called a monomer. A monomer is a building block. Do you guys remember the building block stories? Polymers, monomers. This is a monomer. So it possesses what is called a variable region and a constant region. The variable region is the antigen binding site. How many variable regions does this monomer have? 2. So how many antigens can it bind? 2. Absolutely. Now the constant region is what gives us the class. It tells us what class this antibody belongs to via the constant region. So more like this area right here always tells us what antibody class we're dealing with. It's easiest to look at that heavy chain for that. We call our monomers, our Y-shaped antibodies, bivalent because we have 2 antigen binding sites. And that stem region is also referred to as FC. And it's called FC because it's involved in that classical activation of complement. FC, or the stem. We'll stop there. And what I'm going to do is I'm going to create a lecture. That's a supplemental lecture for this material, because I want to have it available for you guys to study over the weekend. We will not cover the rest of this chapter the next time we're together. So if you have any questions, you need to ask me at the beginning of a lecture on Tuesday. The reason I'm doing this is because I have a path that I want us to follow to where you guys are done earlier in the semester instead of all the way to the end. So I'm going to stop talking right now before I cough.